Okay, let us begin. All right, we have a function f of x equals x squared, interval 0, 2. Let's take a look. What's that?
Is it x cubed or x squared?
X squared.
Oh, this is the review.
No, this is your test.
I know.
Oh,
We're reviewing the test.
yeah, we're going over the test. Yeah. Would I give you an x cubed in your test? Would I make you a special test?
This might have been, I don't know, it says test 4. But it might have been, it might be the review.
Oh, is it multiple choice?
It's pre-test 4.
Oh, pre-test, all right.
Yeah.
Never mind.
Okay.
Sorry, you two.
All right, we have this interval from 0 to 2. This is the slope of the secant line here. And we're looking for that c value between 0 and 2, where the slope of the tangent line is equal to the slope of the chord. There is such a c. We know there is such a c. It's guaranteed to us by the mean value theorem. So, step 1, find f prime of x is 2x. F prime of c is going to be 2c. We want to find that c where f prime of c, slope of the tangent line, is equal to f of b, b being 2 minus f of a over b minus a. So we want 2c to be equal to f of 2, 4 minus 0 over 2 minus 0 equals 2. Divide by 2 to get c equals 1. When c is equal to 1, the slope of the tangent is equal to the slope of the chord. So let's see. The questions are, number 1, f prime of c, 2c. That's b is the answer. 2. Find c where the slope of the tangent is equal to the slope of the chord. That's c equals 1. Okay? And that would be b as well. And that's it for that one. All right.
Wait, how is C1 again?
Because 2c has to equal 2. Divide both sides by 2. Okay? 3 through 6, you're given a polynomial. F of x equals x cubed minus 3x squared. And we have to find various things here where it's rising, horizontal tangents, concave up, point of inflection. So, let's take the derivatives. First derivative. Let me factor out a 3x. And let's graph this first derivative. Because if you can graph the derivative, you know everything there is to know about the derivative, okay? This is a parabola. It's concave up. It has a 0 at 0 and a 0 at 2. And it's concave up. It tells me everything I need to know about that derivative. Where it's positive, x is less than 0, x is greater than 2. Where it's
the graph was like that? I'm sorry.
It's all right, because it's a parabola, 3x squared, it's an x squared. The coefficient of x squared is positive, so you know it's concave up. And I know it has zeros at 0 and 2. Those are the x values that cause the function to be 0. Okay? Okay, so I know everything there is to know about the first derivative. The second derivative is 6x minus 6. That is a straight line. 6x minus 6 looks like this. It hits here when x is 1. Okay? So, let's answer the questions. Where is the graph rising? The graph is rising when the first derivative is positive. The first derivative is positive when x is less than 0 or greater than 2. Okay? Horizontal tangents. Horizontal tangents occur where the first derivative is equal to 0, at x equals 0 or x equals 2. We have horizontal tangents there. Okay?
Wait, so which graphs do we look at to see if it's rising? Both?
The first derivative is the graph you look at to see if the graph of the original function is rising. Where the first derivative is positive, and the first derivative is positive when x is less than 0, because it goes above the x-axis, or x is greater than 2. That's where the first derivative is positive. That's where the graph of the original function is rising. Damien?
So the first derivative tells us rising, falling, and the tangents.
Horizontal tangents, yes, it does. Okay, is everybody else set on that? We got here. Let me plot the function itself. And the way to plot the function is to use these horizontal tangents. When x equals 0, I've got a horizontal tangent line. How do I know that? Because the first derivative is 0 there. Okay? And also at 2. And if I take the 0 and substitute it into the original, my function is 0. At point 0, 0, I have a horizontal tangent there. Let's take x equals 2. When x is equal to 2, my function is equal to 8 minus 3 times 4, 8 minus 12, negative 4. At 2, negative 4, I also have a horizontal tangent. I have a graph that's rising when x is less than 0. A horizontal tangent at 0. It's falling. I didn't ask for that, but it is falling between 0 and 2. It's where the first derivative is negative. It's falling here. And then what? Horizontal tangent line. Okay? And then it's going to be rising again. This is the graph of my original function. Rising, falling, rising. Okay? Yes?
The horizontal tangents, you look at where the first derivative, where the roots are?
Yes. Yes. Number 5, where the graph is concave up. To find out where it's concave up, take a look at the second derivative. Where the second derivative is positive, the graph of the original function is concave up. Where is the second derivative positive? When x is greater than 1. X is greater than 1, this second derivative is above the x-axis and is positive. Okay? Point of inflection. Where the first derivative is equal, a second derivative is equal to 0 at x equals 1. Now, when x is equal to 1, right here, second derivative is 0, the function is equal to 1 minus 3 negative 2. This point right here, 1 negative 2, is my point of inflection. Yes?
So the second derivative tells us concave up or down at point of inflection.
Correct.
So just 6 things really.
Yes.
You put it equal to 0, right? To find the
Yes.
inflection?
Yes. And you can see that this point is indeed transition between concave up and concave down. That's what a point of inflection is. Okay? Okay, how we doing? Okay, let's go on. 7 through 12. Oops. Sorry. Now we're given a rational expression. X over x minus 2. And we want to do more or less the same things. But now we've got asymptotes to consider, which we didn't have in the polynomial function. Polynomials don't have asymptotes, vertical or horizontal asymptotes, ever. But rational expressions often do. Okay, so let's take a look. We still want to find the first derivative. And to do that, we're going to use a quotient rule, denominator, derivative of the numerator, minus numerator, derivative of the denominator, all over the denominator squared. Drop the grouping symbols, x's will cancel, we'll get negative 2, x minus 2 squared. This is our first derivative. Here, I might as well let me do the second derivative as well. Second derivative. Now, the thing to do for a second derivative is not to use the quotient rule. You got a constant here. Think of this as negative 2, x minus 2 squared. Take the derivative here, take the 2 out front, that gives you a negative 4.
Negative 2, because it's in the...
Negative 2, yes, thank you very much. And that'll be a positive 4, thank you. And subtract 1, and take the derivative of x minus 2, which is just 1. So there's nothing to put out here. If this had been a 2x minus 2, for example, there would be a 2 coming out here. So you get 4 over x minus 2 cubed. There's my first and second derivatives. First derivative, second derivative. right. What about these things? Well, let's take a look. The first thing we want to do is where the graph is rising. So where's the graph rising? Where the first derivative is positive. Now, take a look at this first derivative. The numerator is negative 2. It's always negative. The denominator is always positive except at 2, where it's undefined. Negative over positive is always negative. It's never positive. This thing is never positive. So rising, never. Okay? Falling. Always, as long as x is not equal to 2. Because at 2, the thing is undefined. But every other value, the first derivative will be negative. Horizontal tangents. I'm answering, I don't know. We'll have to look at the questions to see what the questions actually ask you for, but I'm doing them all. Horizontal tangents occur where the first derivative is 0. This first derivative is never 0. The numerator is negative 2. Okay. Let's do concave up. It's concave up where the second derivative is positive. Well, let's see. Numerator is positive 4. Denominator is x minus 2 cubed. Well, that's going to be positive if x is greater than 2. If x is greater than 2, x minus 2 is positive. Cubing that is positive. We'll have positive over positive, which is positive. So x is greater than 2. This will be concave up.
So by looking at the second derivative, what do you look for? If it's positive, or it's positive?
Positive, you want to know where the second derivative is positive. That tells you where the graph of the original is concave up. Where the second derivative is negative, we have a graph that's concave down. And where is this negative? Well, that's always positive, the numerator. This is negative when x is less than 2. Point of inflection occurs where the second derivative is equal to 0. Well, the numerator here is never 0. There is no point of inflection. Okay? We can draw the graph. Well, let's do vertical asymptotes. Then we'll do the graph. Where do vertical asymptotes occur? At those x values that cause the denominator to be 0 at x equals 2. We've got a vertical asymptote. Horizontal asymptote. Take a limit as x goes to infinity. Now, here's the rule. If the numerator is greater degree than the denominator, there is no limit. It will go to infinity or a negative infinity depending on the sign. If the denominator has greater degree, that limit will be 0. Okay? And you'll have a horizontal asymptote, y equals 0, the x-axis. If they're of equal degree, which we have here, that limit is the ratio of the leading coefficients. Leading coefficients here are 1 and 1, respectively. That ratio is 1. We have a horizontal asymptote at y equals 1. Jeff, you made it! Attaboy. We're going over the test.
Question.
Yes.
What if it was sin x over cosine x?
Whoa! If we had sine x over cosine x, for example, and we're taking a limit as x goes to infinity, first of all, that's tangent x. Tangent x as x goes to infinity, there is no limit, okay? Because tangent goes like this, goes like this, goes like this. There is no limit.
No limit, so it's infinity?
No, it's no limit, and you can't even say there is no limit because it goes to infinity. There is no limit because that tangent is periodic like this. It changes all the time. So there is no limit. There's simply no limit. There's no one value that it approaches. This would be no limit at all. Okay? All right, let's do the graph of this expression, and then we can answer all the questions. Okay. We have a vertical asymptote at 2. It's probably the place to start when you're doing a graph of these things. We got a horizontal asymptote, y equals 1. Now, graphs may cross horizontal asymptotes. It's possible that they do. The horizontal asymptote is telling you the behavior of the function as x increases without bound and x decreases without bound, okay? All right, that pretty much defines where this function is going to be, however. So what do we know? We have a graph that's never rising, always falling. Always falling. That tells you right off the bat what the heck this thing looks like, okay? You should get the y-intercept when x is 0, y is 0. So it goes through the origin, and it's always falling. Okay? If it's always falling, it must look like this on that side, this on this side. And let's check it with the second derivative. Concave up when x is greater than 2. Yeah, that's concave up. Concave down when x is less than 2. Yes, it's concave down. Falling, falling. No horizontal. That's it. Okay? That's it. All right, so the answers to the questions are 7, where the graph is rising, nowhere. Falling all the time as long as x is not 2. Horizontal tangents. What? We have no horizontal tangents. There's no place where the first derivative is equal to 0. Danny?
For the concave thing, what was the answer to it?
Well, 10, concave up when x is greater than 2.
Never mind. I was into the wrong question.
Okay, it's all right. So 10, x is greater than 2, that's C. 11 is a vertical asymptote, x equals 2, that's also C. Horizontal asymptote is y equals 1, again, C. Wow. Burns is in a rut, all right.
I'm guessing he likes giving C's.
No, I don't like giving C's. The only grade I like giving is an A, okay? It's the only grade I like it. All right, no problem. 13 through 16. We're going to maximize the product, x cubed y, where x plus y equals 100, and x and y are greater than or equal to 0. First thing you want to do is find p in terms of one variable. We're going to do it in terms of x. To do that, solve for y and substitute it in here. Okay? There's p in terms of a single variable. I mentioned this before. When you get to Calc 3, if you take Calc 3, the best course there is in the world, all right? You have to get that in terms of two variables, okay? But we're doing it in terms of a single variable. So we can do it, that question is B, 13 is B. Then it says to find critical values. Well, you find critical values by locating those points where the derivative is equal to 0, or where the derivative does not exist. But we've got a polynomial, so the derivative exists everywhere. So let's take the derivative. Set it equal to 0. I'm going to factor out a 4x squared. I'm going to get 75 minus x. I have two critical values, x equals 0 or x equals 75. Those are my two critical values, 0 and 75. That answer is A.
Wait, how did you find that derivative?
The derivative, I did the derivative of 100x cubed, brought the 3 out front, dropped this down by 1, brought the 4 out front, dropped this down by 1. X to the n forms.
I just don't get the minus x4.
Which one?
The minus x4, the second one.
Right here. When you take the derivative of x to the 4th, it's 4 comes out front, x cubed.
Oh, you distributed it, okay, I see what you did.
And then I took the 4x squared out of each one. Yep. Okay. Everybody all set? Okay. Okay. 15. We want to find the x that maximizes the product. Well, we have two critical values. Well, it's pretty clear that x equals 0 is not a solution because that product is 0. And we can do better than that.
What'd you just say?
It's pretty clear that x is not 0. That would give us a product of 0, and that would not be the solution. X equals 75 is a candidate for the solution. It's the only viable candidate there is. How do we tell that it is indeed a maximum? Well, we do a second derivative. Let's check it out. Let's take the second derivative, which would be 600x minus 12x squared, and let's substitute in the 75 here. When you do that, you're going to get 450,000, geez, all right, minus x squared, 75 squared is 5625. 5625 times 12 is going to be 56,250 plus 11,250. I don't know, what the heck? All right, what is it? I need 12 times 5625.
67,500.
Whatever. Okay, good, thank you very much. And the point is, this is less than 0. Okay? So the second derivative is negative at x equals 75. That tells us we have a maximum, relative max, because it's concave down. So, find the x that maximizes the, well, we knew x equals 75 had to be the solution anyways. Now, 60, yes, go ahead.
Why didn't it be 0 again?
Because 0, when x is 0, the product is 0. Actually, 0 is a solution for number 16. It's the minimized. It's the minimum product when x equals 0. I knew 0 could not be the solution for maximizing this product because I know I can get x and y to give me a product greater than 0. Okay? So 0 can't be the solution for maximizing it. It had to be the 75. But the minimizing solution occurs at 0 when the product is equal to 0. That's it.
So 16 0?
16 is 0, yes. Did you get that wrong?
I get it right.
Oh, good.
No. I made it x equals 100 and you marked it right.
Oh, that's true, because that works too. That's true, that's a good point.
Oh.
I'm glad you mentioned that, because here's my x values. X can be from 0 to 100. Those are my endpoints, 0 and 100. 0 is the obvious choice here for a minimum. But if you let x equal 100, what's y equal to?
0.
0. And that also gives you a product of 0. So that also gives you the minimum value. It's not what I was thinking about when I first made this thing up, but I think it was you, Danny, when I looked at your test, it dawned on me that that does
That's
work.
what I thought.
Yeah.
I know I came up with it after we told you.
Oh, never mind. It wasn't you at all, Danny.
I
Forget it.
have a question. Could you also say that 75,
What's that?
could you also say that 75 maximizes the product? Because if you choose between x equals 0 and x equals 75, 75 is obviously bigger, so it would maximize.
Ooh, that's not good logic. Just because the x 75 is greater than the 0 doesn't mean that 75 necessarily will give you a bigger product. Because it's possible that the y, on the other hand, will do it.
Yeah,
Okay.
I get what you're saying.
Yeah. Damien?
So if we get a negative for the second derivative, that would give us our max value?
Yes.
And if it's a positive, that would be the minimum?
Yes, it's correct. Okay. Everybody all set with that? Okay, 17 through 20. Rectangular fence is to be constructed. All right, here's a farmer question here.
See if we can make this in 5 minutes increment.